We are continuing our talk about forces. In this video, we're going to work a couple of example problems that are pretty standard. We're going to start with the elevator problem. We are interested in the forces acting on the guy in the elevator. Let's start simple. Let's say the acceleration is 0 meters per second squared. So our first step is going to be to draw our free body diagram. Now, if you'll remember, a free body diagram is a picture that shows all of the forces acting on an object. So the object in this case is our guy. I'm not a great artist, so my guy is just going to be a circle. We know that the weight of the guy is pulling him down. We'll call that F sub g. And we know that the floor of the elevator is pushing him up. And we call that Fn for the normal force. The normal force is any force applied by a surface perpendicular to that surface. In math, normal actually means perpendicular to the surface, so it's a math word. If it was up to me, I would call it the force that is perpendicular to the surface, but we are stuck with calling it the normal force. Okay? So in these problems, you'll usually be asked to either find acceleration or find the magnitude of one of the forces. Since we know acceleration, let's find the normal force. So I write down Newton's second law. The sum of the forces is equal to mass times acceleration. So I have two forces acting here. I'm going to say that my normal force minus my weight is equal to my mass times acceleration. So in this case, I said that because the weight is pointing down, I'm going to call that one negative. In this case, it doesn't matter. We'll talk about more about that in a second. So, my acceleration is 0, so that the ma term ends up being 0. I rearrange, and I get that my normal force is equal to my weight. So 80 times 100 meters per second squared is equal to 800 newtons. So in this case, where the acceleration is 0, my normal force is equal to my weight, which is 800 newtons. So that one was super easy. Let's do one with an actual acceleration now. So same elevator. Let's say that it has an upward acceleration. So maybe this elevator starts at rest and then it speeds up. So it's going to go upward. We start again by drawing the free body diagram. There's my dot, there's my weight acting down, and my normal force acting up. And for good measure, let's put the acceleration on the side pointing up. So I'll write my Newton's second law. Sum of the forces is equal to mass times acceleration. I'm once again going to call my normal force positive. It happens to be in the same direction as my acceleration. So normal force minus the weight is equal to mass times acceleration. So acceleration here isn't 0, acceleration is 5. Again, we're going to solve for the normal force. So let's rearrange. My normal force is equal to mass times acceleration plus my weight. Plugging in the numbers, I get 80 times 5 meters per second squared plus 80 times 10 meters per second squared. And I get 400 plus 800. The total normal force is 1200 newtons. So this is bigger than just the weight. Let's think to ourselves, does that make sense? If I'm going up in an elevator, so the magnitude of my normal force is greater than my weight. When we're going up in an elevator, if it starts really suddenly, you might feel your knees buckle. That's because the normal force is suddenly bigger. We feel the floor of the elevator pushing harder against our feet when the elevator is accelerating upward. So that makes sense. We also know, looking at this free body diagram, in order to get it to move, the force upward has to be greater in order to get that 5 meter per second acceleration. So we've taken care of the up. Let's talk about what happens when the elevator goes down. So let's say that the elevator's accelerating downward at 5 meters per second squared, same as before. I start out. So this one is a little weird. When I draw my free body diagram, my acceleration is going to be pointing downward. We always want to set our positives and negatives based on the direction of the acceleration. So we're always going to say that whatever direction the acceleration is going to be positive. It's weird, it's kind of counterintuitive, but it's going to work out better in the end. So, my free body diagram. My weight, I'm going to say that that's a positive mg. My normal force is going to oppose it. So when I write down Newton's second law, the sum of my forces is equal to mass times acceleration. I'm going to say a positive weight minus a normal force is equal to my mass times my acceleration. So we're going to solve again for the normal force. I'm going to do some algebra here. Adding the normal force to both sides, subtracting mass times acceleration from both sides, I get that the normal force is equal to my weight minus my mass times acceleration. Now I plug in my numbers. 80 kilograms times 10 meters per second squared minus 80 kilograms times 5 meters per second squared. I get 800 minus 400. So my total normal force is 400 newtons. So the normal force for an elevator accelerating downward is less than my weight. Well, I think this is the best part about elevators. When the elevator is accelerating downward, the normal force acting on my feet is less. So the force pushing upward on our feet is less than what it is normally. So that kind of gives you the feeling of almost being weightless in an elevator. Hopefully you don't actually feel weightless in the elevator, because that means the cable has snapped and you are plummeting to your death. That's very unlikely. I don't think anyone has ever died from it. I checked Wikipedia just to make sure. So this makes sense. If you're accelerating downward, you experience a less normal force. If you had a bathroom scale in the elevator with you, it would read less. So, that's it on elevator problems. We're going to talk about another type of problem that we'll see a lot, coupled motion. So, as the name sort of implies, coupled motion describes what happens when two or more objects are tied together, stuck together, somehow fastened together so that they all move as a unit. Okay? So, I'm going to draw a familiar picture. This looks kind of like the lab y'all did a couple days ago. So the green block is the cart, the blue block is like the mass hanger, and there's a string over a pulley. So the key point that you may have got from the lab is that all of the objects that are stuck together, tied together, whatever, they all have the same acceleration. And this makes sense because, however fast one is going to move, the other one's going to move because it's stuck together. So all of these objects have the same acceleration. This is a critical point that would be very, very good to remember. There's two ways we can go about doing this. The hard way is called adding systems of equations. It even sounds hard. It's not super important that you necessarily get this. Those of you who are math inclined, you might like it. So, those of you who are math inclined, here are some masses. The mass of the mass hanger is 2 kilograms, the mass of the cart is 3 kilograms. If you're going to do this, adding the systems of equations together, the first thing you have to do is draw a free body diagram for both of them. So, I'm going to start with mass 1. There's a tension pulling up and the weight pulling down. Simple. There's only two forces acting on that one since it's hanging off the edge. For the green block, the cart, there's the weight and the normal force. So the force of the track pushing back up on it. and then there's also the tension in the string that's pulling it, in my picture, to the right. So just like in the elevator problem, it helps if you draw which direction your acceleration is going. So for mass 1, it is accelerating downward. For mass 2, it's accelerating to the right. The next step is going to be writing your equations for both of them. So for both. Alright, so for mass 1, this is going to be in blue. Sum of the forces is equal to mass 1 times A. You have to treat the masses separately. So the two forces acting on it, tension upward, weight downward. Since my acceleration is downward, my weight is the one that needs to be positive, and my tension needs to be negative. So the weight minus my tension is m1 times A. Just rewriting that again, m1 times G minus the tension is equal to m1 times A. That's the equation for block 1. For block 2, the sum of my forces is equal to mass times acceleration. My weight and my normal force cancel each other out. The cart doesn't experience any motion, any vertical motion at all. So those two just cancel out completely. And the only force that ends up acting is the tension. Now, since my acceleration is to the right and my tension is also to the right, I make that positive. Okay? And that's all I have for that one. There's only one force, one net force acting. The third step, okay, so there's equation 1, equation 2. The third step is to add them together. So my first equation was m1g minus tension is equal to m1a. My second equation is positive tension is equal to m2a. And I just add these together, sort of like normal. I get m1g plus 0 is equal to m1a plus m2a. I rearrange a little bit, the 0 goes away. I'm going to factor the a out, so I get m1 plus m2 times a. I'm solving for a this time since I don't know it. A is equal to m1g over the sum of m1 and m2. Whew. So, I did give you some numbers earlier. Mass 1 was 2, and mass 2 was 3. Plugging that all in, we get that. So if we don't have numbers, we use this one. If we do have numbers, I mean, obviously you plug it in, and in this case we got an acceleration of 4 meters per second squared. Ugh, that was the hard way. So I have good news. The easy way is much easier. The first time I saw it, I thought it was a little weird, but I think that most of you will like it better. So essentially what we do for the easy way, this is kind of going in like 2 dimensions, right? The green mass is moving to the right, the blue mass is moving up and down. It's a little complicated. That pulley really just messes things up. So let's get rid of the pulley by moving mass 1 over and making it in 1 dimension. So redrawing our diagram, we have m2 still connected to m1. So this gets rid of that right angle turn. Now we have to put all the forces back where they should be. So for mass 2, we have the weight acting down, the normal force acting up. Those two are going to cancel out, we know that. And then it's also got that tension acting to the right, like we showed in just a couple minutes ago. Alright, and then for mass 1, since this has shifted, essentially rotated 90 degrees, we are going to have a tension acting to the left, and then what used to be its weight will be acting to the right. So I essentially just shifted that 90 degrees. And then our acceleration is going to point to the right. So, fortunately, a lot of stuff cancels out. The normal force and the weight for the green block will cancel out. This is really cool. The tension in the string This is a Newton's third law action-reaction pair, so the tension pointing to the right is M1 pulling on M2. The tension pointing to the left is M2 pulling on M1. So we know that these are equal and opposite, and that goes away. Now we can redraw our diagram yet again. I know it seems complicated, but you're going to like this. So we get M1 plus M2. We can just say that these two blocks are stuck together, because, in coupled motion, they are essentially stuck together. Now, what's the only force that's left? It's just M1G. We will write our Newton's second law. Notice that when I use the mass, it's M1 plus M2, because now we're treating it as a solid block. And the only force acting on it is M1G, pointing to the right. So, solving for A, we find that we get the exact same thing that we got before. You can check me on that. M1G over M1 and M2. And just to double check with our numbers, 2 times 10 over 5 is 4 meters per second squared. Don't worry too much if you didn't catch the hard way completely, and don't even worry too much if you didn't quite follow this all the way through. We will be working plenty of examples in class, and you'll get plenty of practice in.